welcome to another video where today I would like to talk about something that has baffled me. Now, I've watched this video before because it is extremely short, and in there I found one of the silliest things I think I have heard say before. So this is quite remarkable. Now, it is from a channel that I did previously not know. It's BMLSB69, nice. And it was recommended for another video by Taboo Conspiracy, so you already know that it's probably full of... I'll leave the rest of you to the imagination of the dear viewer here. So, what's going on? What am I talking about? Let's have a listen. So it's definitely about parallax, right? I will give an own explanation of what parallax is briefly at a later point. Now that is not true. I did think about it previously, but that is not the content of this video. So the point that they're making here is that you have two mountains and then you have the city of Portland. And as you move to the side, as it would be expected, the background object moves less in terms of angle than the foreground object. Naturally. Now, I would like you to keep in mind how far they move here, right? So they move a good bit to the side here. I would say maybe half, maybe a little bit more of the distance from Portland to Mount St. Helens. I hope I got the mountain names correct. I think that's about half the distance. That's fair, I'd say. And now he says that the distance between Jupiter and Saturn with respect to the Earth are similar to that of Mount Rainer. Now in German we would call this Rainer, but I don't think that this is a German mountain. So I think I've heard people refer to this mountain previously as Mount Rainier, maybe something like that. Regardless, between the two mountains is similar to Jupiter and Saturn, right? So that Jupiter is roughly half of the distance from Earth than Saturn. Not exactly. It's like 40% or something like that. As I said, about half, if we're gracious for purposes of demonstration. Let's say half, okay? And now comes the thing that baffles me. That gets me. So when you look at the night sky, there is no parallax in between them, in between the two stars. Now there obviously shouldn't be. Different topic, right? There shouldn't be one because Earth is rotating, and parallax really doesn't apply to rotation. But you know, I mean that there shouldn't be one within a night. Of course, within a year or something like that, there would be. If Jupiter and Saturn weren't also moving, which is not an ideal candidate for parallax if both move, which is a little, you know. I also like the fact that they use 2 periods here, because why use 3, you know? Budget cuts and all. Now, that was true if we were moving significantly within a short amount of time with respect to the stars, and the stars were still, or the planets in this case were still, then yes, this would be possible, but we aren't moving a sizable amount compared to the distances that we have here, and we're also rotating, and the perceived movement in the sky is due to rotation. Okay? And parallax does not apply to rotation. So I hope we're cool with that now. almost as if the ground you were standing upon was slowly rotating. Bizarrely, huh? That's, oh my god, very bizarre. Very bizarre, that. That's a keen observation there. Now, I've heard this point being made previously by, I think it was Pitch Lumen. I made a video about that, where I showed in the staff room of where I volunteer that I moved my phone. I rotated my phone without changing its position to the best of my ability, and obviously, parallax doesn't apply to rotation. Like, obviously. I would like to, now that I realize this I've just noticed now this video is a year old and we have 2 offs in the title. Amazing. And you know, it's the same with Mercury and the Pleiades. Even though the Pleiades are very far away, Mercury compared to that is not very far away. Almost as if they were comparatively stationary, not absolutely stationary. They have their own proper motions, but in short terms you won't notice that because the rotation causes a way bigger shift in apparent position, right? So, you know, almost as if the ground you are standing upon is rotating. Now, sometimes when I'm at university or when I'm doing stuff for the paper, which is still not released yet, sigh, I feel a little silly if I don't get things, right? I discuss with a professor and he says something and I'm like, oh, I didn't catch that, and I read up on it. I feel a little silly sometimes. When I watch these videos, I don't feel silly anymore. Yeah, and I will gladly explain to you why, because somehow I need to explain this to a grown adult. So let's get into it directly. So parallax, my dude. Okay, let's say we have an object here, a blue ball. We have an observer here, and we have a very well determined background, and the observer moves around this line here. At first, this is the top-down view. This is the view from the observer, and at first, when the observer is here, it looks like that. And when the observer moves over, the blue ball seems to have moved. Obviously, it didn't really move. It just appears to move. All right. So this is the basic parallax thing. If we know the distance to the background, or we can, in the case of stars, when we measure background, we say it moves with respect to the stars that don't move, where we can that move so little that the instrument doesn't pick it up. We can suppose them as being infinitely far away, and we can give a rough calculation of the actual distance of the given star or nebula or what have you, which is actually really important. This is also where the unit parallax second comes from, a parsec, which is 3 point something light years, which is the more common unit that is used in actual astronomy, not light years. We don't use light years, we use parallax seconds or parsecs. Good. Side info over. Now, it looks like that, right? That's cool. We like it. Okay, so parallax works if we have stationary objects or one object and a background that is moving, right? That is not moving, right? And if we have an observer that is moving, as we have here, observers on the right here and on the left in the next frame. Okay, then we can measure a shift. Parallax is not ideally measured in objects that are moving quickly. So imagine if this blue sphere was moving rather quickly. Then, of course, the measurement would be difficult, not impossible, of course, if we knew the velocity of the blue sphere. But imagine if the blue sphere is moving and the background is moving and we don't exactly know how fast, well, then it's going to be really complicated to get an estimation here. So that's bad. Parallax obviously doesn't apply to rotation of the observer. If the observer, if I am sitting on a office chair right now, so if I were to move to the side, everything seemed to move in unison. I would ask the creator of this video to do that and then wonder whether the screen that you're sitting in front of and the wall behind it, in my case this is like 4 or 5 meters in my room, are at the same distance, because apparently they move at the same angular velocity. Well, this is bizarre. So by that logic, the screen of my computer and the wall that is 5 meters behind it are moving at the same angular velocity and are thus equally far away. Of course, and if the objects are too far away and we can't measure the parallax angle, well, then we can't really apply parallax, but this is an instrumentation problem. All right, a little bit of mathematics, just as a visualization. Imagine what we're really doing is, let's say we are in front of the object, which is this distance d, the shortest distance between us and a given object, and then we move to the side by a distance of a. Then we have an angle of alpha here. And now, if we would like to calculate the change in angle perceived to us, we would calculate pi half, which is a right angle, 90 degrees, pi half, in radians, of course, minus alpha is equal to, well, pi half minus the tangents of a over d. So if the angle change is constant, if a over d is constant, so for the parallax to be as visible as his example with the 2 mountains, Earth would need to move within a rather short amount of time. The distance, half of roughly, as we said from Google Earth, it looked like he was moving half the distance to the first mountain to the side, would need to move around 250-ish million kilometers, which I find unrealistic. I hope it was kilometers and not miles. Didn't check, but you get the drill. Half the distance to Jupiter. Then we would see it in a short amount of time. Then we would see it, and by short I mean less than a couple of hours, or a couple of hours. So then we would see it as pronounced as it is. Yeah. So the mistake he made there is that he assumed that only the relation to the 2 distant objects needs to be the same, but actually what really counts is a, the amount of space you go over this relative to the distance that it is away. A over d is relevant. Of course, also, if we have 2 objects, which I don't here, I suppose 1 here, then it would also be relevant. But for celestial bodies, the distance a that Earth moves over a short amount of time is way less than d. Right? This is important. Okay, cool. So already, just from that, Jupiter and Saturn are moving, and so is everything else in the sky. So you're kind of picking poor examples for parallax here, particularly with planets that have their own orbit around the sun. Parallax really isn't nice to do because, well, Earth isn't moving that quickly, and typically you do the annual parallax. By that time, when you have waited half a year, Jupiter and Saturn would be at way different places. So this really doesn't check out. This is just silly. But most importantly, and this is a point I would like to emphasize, parallax doesn't apply to rotation. I can't. How can you sit there and talk about parallax and then think that you just turning at the spot, not changing a position, and just rotating at your spot would give us parallax, when you can easily disprove this within your own office, given that you have an office chair, you don't even need one, just stand on 1 foot and turn around. Oh god. Okay, so here, and this is visualized, right? You have an observer on Earth, of course not to scale, obviously, and here is Saturn in that direction, there is Jupiter, and now if you wait 6 hours and you're there, well, the angle is still the same, still is an angle, because the rotation is gives a way more bigger impact on the perceived position than either Earth's motion or the planet's motion, or the planet motions in this case. So this is not applicable to parallax. No parallax in that case, okay? Okay, so now a genuine example, Jupiter and Saturn. I briefly looked up the proper motions that are very similar. So over 6 hours, Jupiter, just from its own velocity, just from its own orbit, would move roughly 0.02 degrees, and Saturn would move roughly half that, right? Which is a bummer. So you wouldn't expect to see a lot of change. Definitely not with the naked eye, and definitely not over short times. You know, this is, you wouldn't expect a parallax to happen here if you don't move very big distances with the Earth or in your spaceship, let's say, in a very short amount of time. You don't expect to see parallax here, my dude, right? Especially not within 6 hours. Ridiculous. So, but we see actual parallax, right? For example, here, Barnard star, you can see the yellow line is a parallax fit, where you can see at which position it was. This is strictly an interpolation. There are more, there are better pictures than this, but this one shows the path so nicely. If everything was heliocentric, it would just be a straight line, but it's not, right? It's not. So on Earth, we see from if we were on the sun, we would see the blue line, but because Earth has an orbit around the sun, we change positions around the sun slightly. Thus, Barnard star seems to be a little bit off when compared to the background every time we measure it. And this can actually be seen with this observation, and then there's the next one, and this goes on so far. You can do this even better if you say you have the displacement relative to position, right? Here's the east-west displacement, and here's the north-south displacement, and then you can see that indeed quite nicely it does that. Yeah. Okay. So this is what actual parallax looks like. The star is moving extremely slowly compared to our actual time for half a year around the sun, right? When the distance is biggest, so it's very, very small, the speed of Barnard star, and it shifts against the background. And Barnard star is actually the best star to do that. You can see it without even measuring it, just from, at the time, moderately good equipped telescopes and photographic plates, where they did a blink test with 2 photographic plates, and they saw clearly that they were quite far apart. So, and with that, I think this is it. Yeah, with the conclusion. So first of all, it's a total strawman. Please try to understand the globe claim before you go on and debunk it. Given that your title has 2 offs in it, and this had been over a year, I wouldn't expect you to actually understand the globe claim. So maybe just put some effort in it. Yeah, and the perceived movement is due to rotation that you show here. It's not due to the motion, but it's a nice evidence of Earth rotation, by the way. So, and with that, I will leave you. I hope you enjoyed this quick and almost dirty one. I hope I could give a little bit of joy. I will hopefully see you in the next video. Until then, have a nice time. If you enjoyed this video, maybe consider subscribing. If you enjoyed it a lot, maybe leave a like. And then, yeah, I'll see you in the next one. Goodbye.